Okay, let's get started. For this exercise, we would like to find out velocities at two particular joints in the 4-bar link mechanism. This is a mechanism we'll be working on. There are 4 links, and the first link, link A, length is 150 millimeters. Link B, 40 millimeters. Link C is 81 millimeters. And then finally link D, 118.015 millimeters. And then we would like to find out velocities at two joints with this configuration. And then at this configuration, angle between link B and link A is 75 degrees. And angle between link A and link C is 70 degrees. And then we prescribe motion 60 RPM, angular velocity at the bottom of link B. So link B rotates, and link C will go back and forth. And we would like to find out V1, which is a joint that connects link B and link D, and V2 joint connect link D and link C. And V1 is actually easy, and so the problem is that what is V2? And then we will find out those two velocities using simulation and hand calculation. And at first, we try to find out two velocities with hand calculations. So to calculate the velocities, we made two little sketches. Okay. And the angular velocity of link BC, which is omega BC, is actually equals to V1 over PB, and also equals to V2 over PC. So we know that V2 equals to PC over PB times V1. Alright. Also from this little triangle, the relationships between the edge lengths and 3 angles will be like this, okay, which is the length of A over sine alpha equals to length of B over sine beta equals to length of C over sine gamma. And alpha is 35 degrees, beta is 70 degrees, and gamma is 75 degrees. Therefore, 150 over sine 35 degrees equals to B over sine 70 degrees equals to C over sine 75 degrees. So, B will be sine 70 degrees times 150 over sine 35 degrees, which is equal to 245.75 millimeters. Similarly, C will be 252.6 millimeters. Now, omega BC will be V1 over 245.75 minus 40 equals to V2 over 252.6 minus 81. Therefore, V2 equals to 171.6 times V1 over 205.75 is actually 0.834 V1. And what is V1? V1 is actually R omega. R is 40, omega is 60 RPM. 60 RPM means 1 revolution per second, therefore 40 times 6.28 radians per second. So it will be 251.2 millimeters per second, which is V1. So V2 equals to 0.834 times 251.2 equals to 209.5 millimeters per second. So we found out V1 and V2 by hand calculation. Now we try to find out those two velocities using simulation. Okay, let's try simulation by SOLIDWORKS Motion. So first thing is to open up the part files for links like we are doing here right now. So link A, okay, drop on the SOLIDWORKS, and here we go. But it's not the crucial part, so we go for assembly. Okay, this is the assembly we want to work on. It's already completely assembled. So now we go for motion study. Okay, selecting motion study 1 tab, and then change the type of study from animation to motion analysis. And in case you don't see motion analysis, please check for the add-ins and make sure that you see SOLIDWORKS Motion checked. Otherwise, you will not see the motion analysis in study type selection. Okay. Now we need to set up a motor, and that is the only thing we need to set up. And make sure that rotary motor is selected, that it's default. Okay. Change the speed to 60 RPM. And then we need to set up the motor that will be at the hole, bottom hole of link B. Now we see the direction, it is clockwise from this view, but I want to make it counterclockwise. So change the direction with this toggle. Okay, reverse the direction. Now you see the arrow in the counterclockwise. Okay, check, and it's okay. And then I would like to run this job for 10 seconds, so change it from 5 to 10 seconds. And basically, that's it for the preparation. Okay, so let's run. Here we go, calculate it. Oops, it's quite fast. Wanna replay it. So let's replay. Well, motion looks good, looks no problem. So next thing is to find out the speed of each joint. The left one, that V1, and the right one for the V2. So how we do that is actually simple. Click on Results and Plot. Then select the category for displacement, velocity, and the acceleration. Then we need to select for the subcategory, and that will be linear velocity for this case. Then we select magnitude. We want to find out the magnitude of that linear velocity. The location is that face of the pin. Okay, and then this will create a plot versus time. Okay, speed versus time. So click on the check mark. It's a little change in speed, but basically 251.3 to 251.7. So basically we can say that 251 millimeters per second. Want to export that to CSV. Okay. Save it in the whatever the location is. And I would like to open that CSV file, and it says basically 251 millimeters per second. So we confirmed that simulation results basically same as the hand calculation result. It quite looks good. So next thing is that try to find out V2. So close that Windows, and again click on Results and Plot. Displacement, velocity, acceleration, linear velocity, and magnitude. Then select on that face of right pin. Okay. Now, this time the velocity changes quite a bit because it's swinging, you know. And then the right hand angle 75 degrees in the right hand angle 70 degrees. I mean right hand 70 and left is 75. So basically 0 second, 1 second, 2 second, 3 second, because it's 1 rotation per second. So want to look for that number. And from this graph it is hard to see the exact number. So what we need to do is click on the graph and export to CSV and save it. And again, open it. Yes, it's 209.6. Not exactly same as hand calculation, but basically in the range. It's 209 millimeters per second. So again, we can say that we confirmed that simulation result is equal to hand calculation results. So that's it for this exercise. Thanks for listening, and then please try for different cases by yourself. Thanks. Okay, now let's try it with Autodesk Inventor, actually dynamic simulation in it. Okay. Now, I imported the assembly in the Autodesk Inventor and actually reset up the assembly constraint. Okay. So, okay, the other assembly relationship basically same as the SOLIDWORKS. So now we open up the dynamic simulation window. Okay, it seems that there will be no redundancies, so it's okay. And then the way to set up in the Inventor, it's different from a SOLIDWORKS simulation. We set up like motion and stuff in the each joint. Okay, so we would like to find out information in joint 2 and 4. 2 is on the left side and 4 is in the right side, means B1 and B2. Okay, so let's do it. We define the motion in the joint 1, open up the profiles, and then set up for the impulse motion, and then check on enable impulse motion, and then default it's velocity, but we need it for constant value. Okay, degrees per second is the way to define it. So again, what we would like to define here is 360 degrees per second. Okay, and it's okay. Alright, basically this is the only definition we have to make. Okay, then again, make it 10 seconds. Alright. Okay, let's play it. Well, this is clockwise motion, but remember that we need counterclockwise motion. So we have to modify that definition. Okay, go back to construction mode and then reopen the properties. Okay, so make this minus 360 degrees like this, and make this will make the rotation counterclockwise. Okay, looks fine. Okay, now let's try to find the velocity in the those joints. So set up trace, trajectory, and velocity for the left pin for V1, and apply it. Okay, this is trajectory. They should be circle, obviously. Okay, and then let's try to find the velocities, but before that, okay, do the same thing for right joints for V2, and okay, this is the trajectory. Make sure that this will swing, not rotate. Okay, so output grapher, and then this kind of graph and other window opens up. Okay, so check for traces and open up trace 1 and trace 2, and then velocities. Okay, check for V for pin 1, and then yeah, it should be constant, 251.327. Basically it confirms a number in the hand calculation. You can export it to the graph as well. Yeah, like this, to the Excel file. We can confirm that 251.327. I would like to save it for like B1. Okay. Alright, so we confirmed V1. So now we would like to find out V2. Yeah, basically similar graph as we did in SOLIDWORKS, obviously, and then check for the value. Yeah, 209.6. This number confirms the hand calculation value as well. Yeah, so again, we would like to export it to the Excel file, and again we can see that number. Okay, for the Inventor simulation, dynamic simulation, basically that's about it. If you're Inventor user, please try this dynamic simulation. You should find quite interesting and try for different cases. Thanks.